Well, thanks very much, Martin, for the very kind introduction. Also, thanks to all the organizers for having me give a talk at this fantastic conference. And indeed, what I'm going to show you is one of the experiments we did over the past months or years about spectral evidence of squeezing in a driven nonlinear nanomechanical resonator. And as you've just heard, we're in the process of relocating between Konstanz on beautiful Lake Konstanz to Munich, actually geographically not particularly far, but moving labs always takes time. And hopefully after the summer, we're going to set up our offices in this new, first new building of the new electrical engineering, well, zone out in Garching. So this implies that most of what I'm going to show you has been measured in Konstanz, but I'm very happy to be in Munich now and also to be part of MCQST. Okay, so this is about nanomechanics. So why do that? Why take care about tiny vibrating objects? Well, I guess the answer is because nanomechanical resonators are viable for a very large range of applications, ranging from classical to quantum ones. And I guess one very prominent example would be sensing. For instance, sensing of minute forces. These resonators are very sensitive just because they respond very sensitively to, many degrees of freedom in their vicinity, for instance, to spins. And that has been done with zeptonewton force sensitivity. A different example would be mass sensing or even mass spectrometry. Again, a nanomechanical resonator is so sensitive because it is so lightweight that it will highly sensitively react to any mass adsorbed on its surface. Single proton sensitivity has been achieved. That corresponds to about 1 yoctogram. And again, that of course offers very interesting applications, even in the classical realm. Now, in the quantum world, this is maybe even more exciting, and this entire field has been kicked off by this experiment from the Andrew Cleland group, which was deemed a breakthrough of the year by Science magazine in 2011. They called this the first quantum machine. Well, but what it really was, it was the first time one of these mechanical resonators, here you can see this little object, almost visible to the naked eye, has been put in its quantum ground state and acted like a quantum mechanical object. So a quantum mechanical object. And this has set off an all new field of science. And actually this field of science is now turning into a field of technology, actually, as it's continuously being exploited for more and more complex purposes. Well, usage can range from quantum devices, quantum sensors. You can find this on the European Quantum Technologies Roadmap. So this is a whole new window opening into a new field and maybe new era. So what are we going to do here? We're going to look at a very simple nanomechanical object, which we're going to use as a model system for maybe more complicated things. What you can see here is a scanning electron micrograph of a nanostring, a long and thin one-dimensional object made of amorphous silicon nitride. The central part, the thin part, is freely suspended. You can see that when looking at the clamping points holding the structure. Such a string would be approximately 50 microns long and would have a cross-section of 200 by 100 nanometers, just to give you an idea. This means the fundamental flexural eigenfrequency would be of order 10 megahertz. And these nanostrings have a very high mechanical quality factor of several 100,000 at room temperature. And that is because this string is indeed a string. It's under very strong tensile stress, which increases the quality factor. In order to control the motion and dynamics of these strings, we use what we call a dielectric scheme. We don't want to metallize the string because that would introduce a lot of extra dissipation. We would lose the high mechanical quality factor. So we put 2 gold electrodes to the left and right of the string, which you can see here. So now what is important is you have to make sure to place those electrodes such that the string is out of the symmetry planes. of these two gold electrodes, which act as a capacitor. So it's a little bit displaced vertically. You can see that it's below the electrodes. It's also a little bit laterally offset, which is hard to see here in this schematic illustration. This gives us a very good toolbox to control this string, both the in-plane and the out-of-plane mode, which you can see here. For the purpose of this presentation, we'll mainly stick to the out-of-plane mode though. Okay, so how do we control this string? First of all, we can drive its motion by taking advantage of the Kelvin polarization force. This means we apply a strong DC voltage that polarizes the string. It's amorphous silicon nitride, so a simple dielectric. And then we apply an additional radio frequency force, which could be resonant with one of its eigenmodes, for instance, the fundamental out of plane, which I indicated here. And then the polarized dielectric experiences a gradient force in this field, and this has a resonant component with the additional RF voltage and drives our string. In order to detect the motion, we rely on the capacitance modulation between these two electrodes induced by the motion of the little string. And as this is very small and hard to detect, we take advantage of a microwave cavity. Here you can see a photograph. So this is a λ/4 microstrip operating at room temperature, which is bonded to one of the electrodes. We pump this microstrip cavity on resonance to observe sidebands modulated onto its resonance by the moving string. And those are demodulated, and we can use this heterodyne cavity-assisted detection scheme to resolve pretty small displacements. We can also use these two electrodes and the voltages applied to them to control the eigenfrequencies, the dissipation rate, coupling between modes, but all of that isn't going to be in the center of what I'm going to tell you today. So what we've done in the past with this system, we've operated a lot in a regime where the out-of-plane and the in-plane modes were coupled, strongly coupled by means of this electrical field between the electrodes. And we've done a lot of Landau-Zener physics, Rabi and Ramsey sequences, also Stückelberg interferometry. But today I'm going to like to show you something else. And what I'm going to focus on is a single mode, as already pointed out, no coupling to other modes, but a single mode which is driven slightly more strongly to enter the nonlinear regime. And here's what I'm going to do. First of all, I'll give you a brief outline of how a nanomechanical resonator operates and can be thought of in the nonlinear regime. This is mainly about the Duffing model. Then I'm going to show you how we can observe squeezing, generate and observe squeezing in the sideband resolved regime of such a nonlinear resonator and how that can be detected in the power spectrum. And in the end, I'm going to show you that this also works in the response spectrum. And that sounds like a minute change, but I'm going to show you in the end that this is actually an important difference. But let's start with the basics. Let me introduce you to the Duffing model. So typically you would imagine the vibrations of such a nanomechanical resonator as those of a harmonic oscillator. Very simple system, harmonic potential, very simple dynamics. But now as you drive this system more strongly, you will at some point start noticing that this harmonic approximation is indeed an approximation and the potential looks more complicated in reality. So you have to consider higher order terms in the potential. And the first one, which becomes important, is this quartic term. In the equation of motion, this reflects as something cubic, and that defines what is called the Duffing model. If you measure the response curve of this resonator, starting in the linear regime where the response is Lorentzian, and then increasing the drive power along this axis in the back, you would see that the Lorentzian starts transforming into something asymmetric, into something which more or less looks like this shark fin. You can look at this a bit more carefully and compare an upsweep with a downsweep, and you will realize that this is actually hysteretic. And there's more than one solution. And that is actually clear because we have this cubic term. So there have to be up to 3 solutions at a particular frequencies. We have this high amplitude solution indicated in red, the low amplitude solution in yellow, and the third solution is this orange one. This is unstable, so it's not possible to operate with that. You can fit this resonance curve, and that allows you to extract the nonlinearity. And then we have characterized our system. We already know all the other parameters, and we're set to go. So when working with such a Duffing resonator, it makes a lot of sense to not stick to the laboratory frame, where the driven resonator would perform a circle in phase space as it oscillates and its energy keeps alternating between kinetic and potential energy. It makes more sense to transform this into the rotating frame, rotating at the drive frequency. And in that rotating frame, the state of this driven resonator corresponds to a fixed point in phase space. Let me already point out that I didn't draw a point. I rather drew a blob, and that indicates that there is noise. As we work at room temperature, this is thermal noise in our case, not quantum limited. We'll get back to that picture. But assuming that we describe our Duffing resonator in the rotating frame, we find that we can describe it by an effective potential, which looks like a tilted Mexican hat. And here you can see a graphic representation of this tilted Mexican hat. You can recover the three solutions, as the two stable solutions are found in the two extrema of this effective potential. The unstable solution would be the saddle point between the two stable ones. Now, were it not for the noise, the system would settle in one of the two stable points, either the high amplitude solution or the low amplitude solution. But we have thermal noise, so the system is continuously being kicked out of this stable point, and it will meander around the stable point and kind of sample the area around it in phase space. And what will be important is the shape of this little potential bowl in the effective potential it is exploring. Again, you can approximate that as a harmonic oscillator. So this potential would be approximately parabolic. And the corresponding eigenfrequency is given by the curvatures of this potential bowl along the two quadrature directions in the rotating frame. This is a slow frequency, much, much smaller than the eigenfrequency, which is at 6 to 10 megahertz. This is more in the order of tens or hundreds of hertz. And now if you step back and imagine transforming your system from the rotating frame back into the lab frame, this slow frequency, omega high or omega low, depending on which solution you're sitting in, will mix on the eigenfrequency, which we drive, and create two sidebands, two satellite peaks. That has been known for a long time. They have also been measured by the group of Ho-Bun Chan in 2006. That's their measurement done on one of these torsional resonators. They had to inject additional noise to make these satellite peaks visible. And I mean, they're barely discerned, but you can see that they're there. So what happened between 2006 and 2021 is that our very high mechanical quality factor resonators came along. And now let me show you our data. Here's what we measure as we drive the resonator on resonance. We increase the drive power on the x-axis, and for every drive power, we take a power spectrum. So the power spectrum, plotted on a color code here, will show a very intense delta-like peak at the drive frequency, which is set to 0 here. But then you can also see these two satellite peaks, which are branching off the first vibrations at the drive frequency, and they come out rather clearly and rather sharply. So we can beautifully resolve those satellites. Let me show you a line cut. Oh, sorry, no, first of all, I would like to show you that obviously we can also model these, and credit goes to our theory collaborators, Mark Dickman, Wolfgang Belzig, and Gianluca Rastelli, who helped us understand that. Besides the scaling with drive power, here comes the line cut. And you can see indeed that these two satellite peaks are equally spaced from the drive frequency. They have the same line width. The line width corresponds to what would be the linear damping rate for the system in linear response to gamma. But what is quite striking is that these satellite peaks have a very unequal intensity. So one, in this case, the upper is much stronger. The other one, in that case, the lower one, is much, much weaker. So what could that be? And now let's get back to the rotating frame picture, which I've already shown you. So usually you would assume that your blob in phase space is broadened. If it's thermal noise which is broadening it, then you know that the equipartition theorem has to hold, and the two variances along the two quadrature directions are proportional to T, the temperature, and they are equal. That is equipartition. And in this effective potential picture, that would correspond to the notion that the curvature of our potential bowl in the tilted Mexican head is the same along the two quadrature directions. Now, if the resonator is a nonlinear one, as it is the case for us, since we're in the Duffing regime, we already know that this is not the case. The curvature of these two directions is not the same. You can even see this in this plot, that the potential bowl is elongated along the x2 direction. And this means, or this reflects that the nonlinear resonator breaks time reversal symmetry. This corresponds to our noisy blob being stretched along one direction, compressed along the other one. The two variances are no longer the same, and we observe a squeezing effect. And actually, our noise cloud looks pretty much like the squeezed lemon. So for visualization. Already pointing out that squeezing can also be a classical phenomenon. Originally, of course, squeezing has been observed for quantum fluctuations back in the 80s for natrium atoms in an optical cavity. Squeezing has, however, also been observed in a classical context where thermal fluctuations are then squeezed to a smaller value than anticipated. This was first done with squeezed microwave radiation with a Josephson parametric amplifier by Yerke, also in the 80s, but also with mechanical systems where the thermomechanical fluctuations have been squeezed. This has first been done by Ruger and Gritter in the early 90s with a nanomechanical parametric amplifier consisting of a silicon microcantilever. But also later on, squeezing has been observed in a nonlinear Duffing resonator, very similar to what we're doing here. We squeeze by driving the resonator in the nonlinear regime, thus breaking time reversal symmetry. Here again, in this group, in the group of EL books, under additional white noise heating, as it were, to increase the noise. What all these experiments have in common is that once the squeezing has been achieved, you need to measure it. And this is usually conventionally done by doing a homodyne detection, by measuring the noise along the two quadrature directions, for instance, by varying the homodyne angle or by completely mapping out the phase space, as it was the case here. So this is a very standard procedure. Unfortunately, it doesn't always work. And one situation where it's not working is the case of a very high Q resonator, because these very high Q resonators suffer strongly from even small fluctuations. And so this is measurements which have been done in the group of Hong Tang. So they wrote a beautiful paper about this. So I'm going to show you their data. Let's assume you have a high Q resonator. You measure the thermal noise at various temperatures. That's the different colors. You see a circular noise cloud. It's getting bigger as temperature is increased. Now you can drive the resonator and perform a sweep through resonance. And then you get this large circle. The situation where you drive directly on resonance corresponds to this point here in the middle of this circle. And if we focus on that, so now we stop sweeping, we just simply pump on resonance. And we try to, again, measure our noise cloud. We should expect to see the same noisy circle, but that's not what we get. So what they find, and we see the same, you find something banana shaped. There's something very elongated. It actually looks like being squeezed, but it is not. This is all in linear response, no squeezing here. And if you look at how these two quadrature signals should look like, you see that the X1 quadrature has this very, very steep section, very close to the resonance. So it will very, very sensitively react to frequency fluctuations, which are unavoidable in these systems. So it's impossible to measure squeezing here because it's impossible to distinguish it from this linear response banana caused by frequency fluctuations. However, the spectral peaks I've been showing you do not suffer so strongly from these frequency fluctuations. So let's see what we can do. Theory tells us that the ratio of these two satellite peaks, once resolved, encode the squeezing angle directly. So let's work this out. It's the same data set I showed you before, and you can see the satellite peaks. We can fit the areas of those satellite peaks for all the different drive powers, compute their ratio, and then convert this into a squeezing angle, or even maybe more illustrative, into the quadrature variances. This is the X2, so the quadrature component, down here in black, the X1, so the in-phase one, and the black line illustrates where the thermal fluctuations according to equipartition should be. So very clearly we have a squeezing effect here, and what we measure, and that is also supported by theory, is that we have 3 dB of squeezing in that system. And what I should also point out is that this theory, you can see the red lines, is not fits. This is simple theory based on a careful calibration of our sample parameters, and it completely coincides with the data. So that is nice. So what can be learned from that? And in order to discuss that, let me switch to the third part, squeezing in a two-tone measurement, squeezing measured in the response spectrum. So what did we do differently here? So we essentially almost repeated the experiment. We have this high-Q resonator. We drive the fundamental flexural mode on resonance. We increase the drive power, but now we are not measuring a simple power spectrum. So now we're not doing a noise measurement. Now we use a second very weak probe tone, which we scan across the resonance, and we measure this response to the weak probe tone. And now that response is plotted on the y-axis and coded, well, plotted along the y-axis and coded in color. And you see a very similar picture. You can see the central feature corresponding to the forced vibrations at the drive frequency, but we can also discern the satellite peaks here. Now, we can use a slightly modified theory. We can again describe the scaling of these satellite peaks with no free parameters. We can again look at a line cut. We discern the central feature and the two satellites. Again, we see that one is more intense than the other. So it seems like we're repeating the same experiment over again with a slightly different technique. Also, this is something which has been done before. Those probe-induced satellites in the response spectrum, they have been observed rather clearly before in the group of Antoine Heitmann and described in this 2012 paper, even though they didn't make a connection to squeezing. But we can do that. In order to do that, and in order to show you why this indeed is interesting and deserves an additional item in my outline, let's look at this more carefully. So when measuring the response, we can look at two things. First of all, we can directly look at the amplitude, which is what I just showed you. The amplitude will give us the response spectrum of this mode. We can also measure the quadratures and either look at the in-phase or the quadrature component of our response. Here is a plot of the quadrature component. And that, I mean, again, shows the two satellites. It shows a central feature. That will measure the imaginary part of the susceptibility, and that corresponds to the absorption of the probe field. Yeah? So, I mean, essentially, in the same measurement, we can directly extract different quantities. And why am I pointing this out? I'm pointing this out because of this lower frequency satellite peak. That has a peculiar shape. It has a dip, not a peak. And that means if there's a dip in the absorption spectrum, it means actually that the probe field is being amplified. So we are pushing energy into the probe field. which is a rather interesting feature. And maybe this could be useful for a couple of things, even though we haven't had a chance to look into this in more detail. But here, I mean, let me get back to the squeezing. From both measurements, amplitude or quadrature component, we can again extract the squeezing angle by looking at the area ratio. And for the case of the amplitude spectrum, we'd have to take the power of 4 of 1/tan of the squeezing angle. For the quadrature component measurement, it's the square root of that, but we can extract the squeezing angle from both measurements. Here's an example for the quadrature spectrum. The area ratio, it's a bit noisy, but we can kind of figure out the value. Theory tells us the area ratio should be 13.9, and this is pretty much what we're getting here. This, if we convert this again into a squeezing angle, we find 0.27, 0.28 in theory and experiment. And we can again convert that into the quadrature variances and again confirm the picture of squeezing of the in-phase quadrature, of the X1 quadrature. Okay, so squeezing works again. Thank you very much. I'm almost done. Essentially, what is missing is the resolution to the question why that is important and interesting to do this over again with the response spectrum. So let me try to summarize. In the classical regime, which is where our experiment was done, we can use the emission spectrum, so only driving and taking a power spectrum to observe these unequal sidebands as long as we can resolve them and characterize classical squeezing as I've shown you. For the case of the response spectrum, so the strong drive and a weak probe scanned along the resonance, we again see these unequal sidebands and we can characterize the squeezing in the classical regime, the squeezing of thermomechanical fluctuations. So in the classical regime, there is indeed not much of a difference, but we could imagine using a mechanical resonator operating in its quantum ground state or in the quantum limit in a more general sense. And in the quantum regime, there is indeed a difference, because the emission spectrum for quantum fluctuations would show equal sidebands. So no spectral information about the squeezing of the vacuum fluctuations could be extracted from the emission spectrum. However, when looking at the response spectrum, we would again recover unequal sidebands. So the response spectrum would allow to resolve vacuum squeezing even for a quantum nanomechanical system. We're hoping to find somebody to do the experiment or eventually to be able to do that ourselves, but this is not the topic of today, so let me conclude. I hope I've been able to show you that nanomechanical resonators in the nonlinear regime are very interesting model systems to learn about squeezed states, how to characterize them, and to venture on from there. And in particular, I've shown you squeezing measurements in the power spectrum and in the response spectrum. And in addition, the response spectrum measurement has this additional feature of the amplification of the probe field. So I don't want to stop without thanking the people who did all this work. Here you can see my group. In particular, I want to point out Jana Ox, who did all the measurements I've shown you today. And I'd like to acknowledge again our theory collaborators, Mark Dickman, who kind of started this together with us, and Wolfgang Belzig and Gianluca Rastelli, who also helped with this work. I'd also like to acknowledge our sponsors, and I thank you for your attention. And this is the conclusion of my presentation.
Thank you very much, Eva, for this great talk, introducing us to yet another quantum system, a quantum mechanical system. Again, I encourage you to send questions via Slack, or if this is too complicated, also to me via email. Allow me to again start with a couple of questions in this Duffing model, in the Duffing oscillator. Experimentally, do you have some kind of a handle to change the prefactor in front of your to the power of 4 term?
Yes, thanks for the question. This is wonderful. Yes, indeed, we do. When talking about our transduction scheme, I mentioned that we can control a variety of quantities with the DC voltage we apply between the two control electrodes. And as a matter of fact, this DC voltage also controls the nonlinearity, which sets the curvature of this quartic potential, or the cubic term in the Duffing equation. So to start with, one always starts out with a positive Duffing constant that essentially is usually determined by what is called the geometric nonlinearity. So this is limited by material and sample geometry. So from elasticity, but there is a dielectric contribution which is negative, and so actually we can reduce the nonlinearity as we increase the DC voltage. We can even make the nonlinearity negative, which would reverse the sign of this shark fin to the other side. Going into the softening regime, we can also zero the nonlinearity, also an interesting operating point. So we have pretty good control on that.
Okay. Your nano beams, are you actually cooling them down? What is the temperature that one should think about there?
So what I've shown you here, so this was all measured at room temperature. In principle, we can cool them down. We conveniently cool them down to 4K, a couple of K. We haven't cooled them down to millikelvin temperatures very often. The reason being these strings, they operate at 10 megahertz, and it's very challenging to get them to their quantum ground state, which is why we haven't done the response spectrum measurement to show the squeezing of vacuum fluctuations in this system. We're still contemplating whether to take on that challenge or whether to switch to a different system. And so these strings are beautiful in a sense that they have a remarkably high quality factor and they're extremely well controlled, but they're not the most ideal system to cool to their quantum ground state. So that is maybe a compromise one has to make at some point. However, hopefully I was able to convince you, we can use them as very powerful model systems to already look at, and maybe even you could call that simulate what would happen with a quantum system under the same controls. But
what would be an ideal?
I showed you was room temperature.
Sorry, what would be an ideal system for a quantum state, or cooling down to to a quantum ground state?
I mean, ideal, it would be ideal to have the same quality factors, 300,000, 400,000, but at an eigenfrequency of, let's say, a gigahertz. Then it would be much, 10 gigahertz would be even more favorable, because then you could stick it in a dilution refrigerator, you'd essentially almost be in the quantum ground state, or you'd already be in the quantum ground state, and you could still take advantage of the large mechanical quality factors. Unfortunately, most high frequency mechanical systems have lower Qs. So that is the compromise I was alluding to. And with a lower Q, for instance, I mean, it wouldn't be as easy to resolve those two satellite peaks. I mean, the detection would be a lot more complicated.
So it's a material system issue? I mean, can we, or is it more or less a fundamental issue? I mean,
the eigenfrequency issue is probably a fundamental issue. So maybe the flexural modes aren't particularly well suited. I mean, we could make them a lot shorter. We could add a lot more tension. Well, not a lot, because we're not too far from the yield strength. There's maybe one order of magnitude in between at most. That is something one could try to push, probably not all the way up to 10 gigahertz. That would be too challenging. But the alternative would be to switch to a different family of modes, which are intrinsically higher frequency, localized modes, bulk modes. But these have lower Qs. And the issue of Q is, of course, a material one and engineering one. But again, taking the opposing approach, starting out with something which has a high frequency but a low Q, pushing up the Q up to a couple 100,000 is also a non-trivial task.
So, thanks a lot. I think we move over to the breakout rooms, or the 3-hour breakout room. let's thank our speaker again with a virtual round of applause. And I guess I have the dubious honor in closing this fantastic MCQST conference as far as the invited speakers and their presentations go. Again, let me join Rudolf in thanking all of you to participate, in particular the fantastic MCQST team who have run this great conference so smoothly. Thank you very much, and see you soon in the roundtable room.